Okay guys, so last time we were discussing electric field and electric field lines, and we discussed that these field lines originate from the positive charge, but they terminate at the negative charge, okay? And we discussed various properties of these field lines. Now, some very important concept about electric field inside conductors. So when you talk about conductors, if someone asks you what about the electric field, remember there are some very important things we need to discuss about conductors. The first and the foremost important thing, whenever you give some charge to a conductor, for example, we have a conducting body, okay? There is a body which is a conductor, okay? It is made up of metal, fine? And you give some charge to this body. The first and the foremost important thing that you have to remember is all the charge will reside on the surface. Charge cannot be present within. Charge is always present on the surface. Is it clear? Because you need to understand, if the charge is kept inside, what will happen? The charge is very close to each other, and when the charges are very close to each other, they repel, and the repulsion causes them to move away, right? So the best possibility to keep the charges is to keep them on the surface, because on the surface we have more surface area, and therefore the charges can be kept at the maximum possible distance. Is that fine? So remember, the first important thing about the charges that you're giving to conductors is that all the charges reside on the surface. Write it down. In case of conductors, all the charges reside on the surface. Okay, point number one. Point number two. See, if you talk about the electric field inside the conductor, if someone tells you what is the electric field inside, if you know what is the definition of electric field, electric field was defined as the force experienced per unit of charge. For example, there is a conductor and it has some charge Q, okay? Now what you do is, you place a small charge inside, small charge, test charge, okay? Inside the conductor. The question is, will this charge experience any force? Yes or no? If this charge is placed inside, will this charge experience any force? Yes. Yes or no? Yeah? All the charges reside on the surface. See, let me ask you another question. For example, you have a charge here. This is its field, okay? And inside this field, what you do, you place a test charge. Now tell me, what will this charge suffer? Repulsion or attraction? Repulsion, right? So there will be repulsion on this charge because it is present inside the field, isn't it? Now when the same charge, there is a body, it has some charge, but this is a three-dimensional body, okay? The charge is present all over the surface, and what I am doing is, I am taking this test charge and placing it inside the body. The question is, will it experience any force? Yes or no? So remember one thing, very important thing. Inside the conductor, the force experienced is zero. There is no field inside the conductor. Remember this thing. No electric field inside a conductor. Clear? Why? Do you know which is the best space to be when there is thundering? Inside a? What is the best place to be when there is thundering and storms? When there is lightning? Inside a car, right? Inside a house?
Yeah.
La.
What do you mean a house?
Mamnu. The best place to be when there is thundering, when there is lightning, is to be inside a sayyara.
Why?
I will tell you why. I will tell you why. There was a scientist by the name Faraday. He introduced the concept of Faraday's cage. Faraday's? For example, this is the person inside the car, okay? Now what happens is, a lot of charge from the cloud comes to the surface, isn't it? But what is car? Car is a metal. It's a conductor, isn't it? So what happens is, it doesn't let electric field inside. When there is no electric field, so there will be no force. So the person inside the car will not experience any electrical force, due to which he is safe. And the concept was called as the Faraday's cage. It acts as a cage and the person within the car is safe. Now the question is why? Why doesn't he suffer from the shock? The best place, remember, to be when there is lightning, there are thunderstorms, is to be inside a car. Not because, yes?
When it's on or off?
The car? Any state, don't worry about that. Because see, I'll tell you. Do you know when current flows, it wants to acquire the shortest path. Do you know that? So what happens is, when the charge from the storm comes, it breaks your dielectric strength of the air and it travels. It wants to reach the ground because ground is at a zero potential, okay? Ground is a sea of charges. It can incorporate the charge. But remember, whenever the charge flows, it flows through the shortest path. Shortest means, if I am standing here and then there is this ground is here, when the charge travels, it will try to go through the shortest path. Shortest means it will not go there, it will try to go through me. Why? Because I am connected to the ground. Is that fine? Is that fine? But when you talk about a car, when you are inside the body of the car is a metal, isn't it? Metallic. And outside it is connected with? It is connected with the ground. So charge cannot enter inside because I told you, conductors have this property that all the charge resides on the surface. The charge cannot go inside. Fine. One more reason to that is, there is something called as the dielectric constant. The dielectric constant for the metals is infinity. That means they break the strength of this field infinite times. They do not let the force to go through. This is the property of metals. Their dielectric strength, their permittivity, relative permittivity is infinite. That means they break the force, they decrease the force, they decrease the electric field infinite times when it has to travel through the metal. Therefore, it doesn't travel. Is that fine? And therefore, remember, the best place to be at the time of lightning is to be inside a car, because it acts as a Faraday's cage. Is that clear? So this charge is inside a cage. It will not experience any force. No matter what is the force from outside, this body, this spherical body, this conductor cages it, saves it from the outside world. It is like a mother's womb. Is that fine?
Yes.
When I was teaching the most important concept,
I had to call my dad.
you left.
Dad, explain again. I want to.
I don't want to explain now. Next, very important thing. Whenever you have to draw electric field outside, so inside electric field is? Inside the electric field is what? Zero. Okay? Now, if you have to draw the electric field outside, remember, the electric field outside is always perpendicular. Always perpendicular, as I have told you in the previous class as well. Is that fine? Clear? That is the concept of conductor. The electric field outside the conductors is always perpendicular. Yes? This is perpendicular.
How do you know that when the outside stops and when the inside ends?
Where?
Like there's the center, right? For the top. The center.
Yeah.
How do you know when that ends and then the outside stops?
Oh, for this?
Yeah,
No. This is a body. We already know this. Here we do not, because we have to go up to the infinite point.
Yeah.
It is the field. Now here we have a charge, and this is a space. Here it is a body. It's a ball, and the charge is present all over the ball. Okay. Inside the ball there is no electric field. Is it clear? Yes. Okay. Now we have a question. Example E. Draw the field lines for the irregular conductor shown here. How do you show? See, all the charge is present on the
outside.
and remember one thing, whenever charge is given, most of the charge is always present at the corners, at the edges. Is that fine? Because here, see, the density of the charge is more, right?
Yes.
Here it is less. Fine. The maximum charge at the edges shows more electric field strength. Is that clear? Okay. So here, whenever you have to draw the field lines, what did I say? Inside the electric field is 0. So there will be no electric field line that you will be drawing inside. All the electric field lines will be outside, but they will be what? Perpendicular. So perpendicular everywhere means like this. And it is a positive charge. From a positive charge, electric field lines are away. Towards a negative charge, they terminate. We know that, right? Because it is positive, so that means you have to draw perpendicular lines outside like this. Is it clear? Is it clear? Yes or no?
Yes.
कुछ तो बात करो.
Sure. What did you say? Say it with us.
Cool. Speak.
Say it again.
In Hindi?
Yeah, say it.
कुछ तो बात करो. Talk. At least for God's sake.
I talked and I told you to explain again.
Oh my God! Listen. What do I have to say? Okay, so I was saying that electric field inside is 0. A conductor acts as a cage. It doesn't let the electric field lines to go inside. It doesn't let the field, the force to go inside. Why? There are two reasons. One, the dielectric constant, the permittivity, the resistance to electric field shown by a metal is infinite. That means it doesn't allow. It won't. It is the property. Okay. Point number one. Point number two is that all the charge resides on the surface. So because it resides on the surface, it is always outwards. It doesn't go in. Therefore, this charge is saved from the outside world. I simply said it acts as a mother's womb, protecting this charge from the outside environment. The best place to be is in a car. Why? Because in a car, the body is metallic. So all the charge will be present on the body, not inside. You will be safe. And that charge will produce electric field, and that electric field cannot go inside because the dielectric constant for metals is infinite again. So that is the best place you won't get. Although it should be a Cybertruck, because if there are buildings falling apart, it can crush the car. So think wisely. Whenever if there is lightning, you want to be in a car, take it into a field. Don't stay near a building. The building will come and collapse, and you will say, Munis sir had told us.
But if I was in my house and I'm safely inside, why would I go outside in the car?
Allah, who told you that house is the best place to be in the time?
My house is safe. I'm inside.
See, here in UAE, I don't think you have all the three connections of wires. I'm not sure. Actually, back in India, we mostly use only two. There are have you seen these sockets?
Yeah.
There are 3 pins, right?
Yes.
1, 2, and 3.
Yeah.
In India, we do not use the top one.
Two you use this.
The bottom 2 are always used. Is that fine?
Yeah.
The top one is not used in India. Why? The reason is this is the ground. This is the earthing. Now, because in Kashmir we are already at high altitude, we do not need it. Okay? But in other, maybe in UAE, yeah, you need it, okay? If your house has this, because whenever you construct a home, there is a proper earthing system. There is a wire which directly goes into the ground. So that wiring is actually doing the same work as the car is doing. Therefore, Hiba's house is safe.
My house is safe.
You're also. Everyone's. In back in India, no house is safe. Because they do not go for proper earthing. Earthing is important because what is the concept of earthing? The concept of earthing, if there is lightning and it strikes your house, okay, the wire that is connected with the ground is a conductor. So what will it do? All the charge will go through that wire to the ground. It will not go inside, you are saved. But in India, we don't do that. That is why our houses, it's better to go out and be in a car. Okay? No matter how cheap the car is, at the end it is still a metal, right? So it's fine. Except some plastic car. Don't be in a plastic car, by the way. Be in a...
What about the electric car?
Electric car is fine. It is still the body. It is about the body. An abandoned car in a garage, which doesn't have an engine, would also work. Because we need a metallic body. Is that fine?
No, wouldn't the battery explode because the lightning?
Batteries inside. Where will the charge go?
Inside.
No.
Maybe for the heavy rain will storms and everything. What will I do? I go to the car?
He said our house is safe. He said no.
My house?
No, our house.
Your house is safe.
Maybe we're in India.
Your house is safe. Don't be in a car. Khalas. Okay, next. One more example. Example F. A point of minus q, there is a point charge, minus q, which is placed at the center here. See? Okay? Of a hollow conducting spherical shell. So this is a hollow conducting spherical shell and there is a charge plus 4q which has been given to this shell. Okay? The question is determine the charge on the inner and the outer surfaces of the conducting sphere and also draw the field lines. Now it is very important. Now I would like to check your understanding of the electric field line in case of conductor. See, minus q is at the center. It has been placed. Okay? Tell me one thing. Will it experience any force? Will this minus q so there will be no field inside. Is that fine? But the total charge present on the outer shell is plus 4q. Okay? Now out of this plus 4q, by the concept of electrostatics, by the concept of the force, plus q will be present on the inner surface, isn't it? Because it will attract, it will get induced because of the inner charge, negative q. Is that fine? So the remaining plus 3q will go to the surface, isn't it? Yes or no? And that plus 3q will be present uniformly all over the surface. Is that fine? And my plus q which is present on the inner side will also be present uniformly. Is that fine? And minus q is present at the center. Fine? Now this is the first concept. The second thing is draw the field lines. How do you draw the field lines in this case?
Is there one going inside because of the attraction that goes?
Or they want to be in a
First of all, how do we draw the field lines for the outside?
Goes outside.
Yeah, something like this. Yes?
Yes.
Perpendicular, very important. Perpendicular and outwards because this is positive charge. Okay? Something like this. Okay? But very important thing. Will there be any field because of plus q here? No. But there will be a field because of minus q. Minus q will generate its own field. Very important. The negative q has its own field. It is the field of this charge and not the plus q on the inner surface. Is that fine? Because charge which is present on the surface produces electric field which is outwards. It doesn't produce electric field which is inwards. Because if that is the case, then definitely you will get the electric shock. Is that fine? This charge will stay there. This will not experience any force. But it will have its own field. And that field can be shown. That field can be shown by the green line. See? It is a negative charge. How do I show the field lines? Terminating at the negative, isn't it? For a negative charge, electric field lines terminate. So it will be like this. See. Very important. These green lines are not there because of plus Q. Very important. They are there because of the minus Q. Minus Q has its own field. This shell is still caging it. It will not let the outside world affect this. Is that fine? Is it clear? Very good. Try to copy it. You may write what I said. So we have almost halfway into the program. Last 3 weeks. Now, let's see what we can. Where is Abdullah Hamdan?
Which one is that?
That no one is there?
What is that?
Okay.
I think the program for what?
Ah, he was saying there is some other program, right? Okay, this completes the concept of the electric fields, okay? Now, we have another important term in electrostatics, and that is the electric potential, okay? The question is, what is electric potential? See, when you talk about heat, if there are two bodies, one is A, another is B, if the temperature of this body is 20 degrees and the temperature of this body is 10 degrees, from which body will the heat flow? From A to B, isn't it? So the direction of the flow of heat, is determined by the temperature of the bodies, isn't it? The temperature of this body is more, so you say heat will flow from that body which has more temperature to a body which has less temperature, isn't it? Similarly, if there are two heights, one is this, another is this, water will flow from top to bottom, isn't it? So the direction of flow of water is governed by the height of the points, isn't it? A to B, right? Similarly, in electrostatics, there is a term called as potential. What does this potential do? It helps you to understand the flow, the direction of the flow of charge. Direction of, yes, flow of charge. From which point will the charge flow? Is that fine?
What's the potential?
Electric potential gives you the direction of the flow of charge. Like temperature gives you the direction of flow of heat, height gives you the direction of flow of water, potential gives you the direction of flow of charge. Is that fine? Is it clear?
Yes.
It is due to potential that you can understand from where to which point will the charge flow. Fine? So, potential is related to potential energy. But what is potential energy? Potential energy is the potential to do work. It is the tendency of a body to perform work. Okay? And is due to an object's position. You know, If I simply ask you what is potential energy, you will tell me it is the energy possessed by a body due to its position, isn't it? At a position, a body has a tendency to perform work. That work, that tendency to perform work is called as potential energy. Is that fine? But this potential energy and potential are very closely related. They are very closely related. In fact, they are one and the same thing, but in different forms. So, in mechanics, an object has high potential when it is higher up, isn't it? And up in a gravitational field. When a body is here, it has more potential energy, isn't it? It has more potential as well. Similarly, in electrophysics, in electric physics, a positive test charge has a higher potential when it is near the other positive charges. Remember this thing. When two charges of similar nature are very close to each other, both of them have the tendency to do work. Do you know what the work is? To go away from each other. So they have potential energy, that's why they repel. Is that fine? So potential energy is the tendency, it is the potential to perform work. When two positive charges are very close, both have the tendency to do work, to perform work, and that work is repulsion, go away from each other. Is that fine? In general, an object has higher potential when it is at a location where the forces will cause it to move away. Remember this thing. Remember this thing. If we say that a body has higher potential, it means it has the tendency to go away. Like for example, I'll tell you, if there are two friends and they fight over something, both have the tendency to go away, isn't it? That means in that situation, the potential energy of between them is high. If the potential energy is low, they will come closer to each other. Remember this thing. Whenever we talk about higher potential, remember the body has the tendency to go away. Is that fine? That is the basic crux of potential. See, for example, we talk about the positive charge. There are positive charges, we say that the electric potential is high. And for the negative charges, very important thing. The negative charges are here. Now this is a higher but negative potential, not the positive potential. I am talking in the language of the positive charges. If there are more number of positive charges here, it means it has a high electric potential. But if the electric potential is low, it means two things. One, we have lesser number of positive charges, or there are negative charges.
Negative or negative charges.
No. I'll tell you. This is in context with the positive charge. If there is positive charge, for example, we have here plus 10 coulomb, and here we have plus 5 coulomb. Okay. So this will be taken as higher electric potential, and this will be taken as lower electric potential. Is that fine? Similarly, if we talk about negative charges, if there are negative 10 coulombs here and negative 5 coulombs here, where is the potential maximum? Higher? Yeah, it is here. Is that fine? Here it is low electric potential, but in physics, we talk about reference, and reference is said to be positive. That is why whenever we say high electric, we always consider it is about the positive charge. So therefore, more positive here and negative here or less positive here means low electric. Positive is high, negative is low. That's what you have to understand. But in reality, it is not every time that positive will be high and negative will be low. Negative can also be high, see. So what we take reference, we take a convention in physics. The convention is take positive as high, negative as low. Take up as up means high, down means low. But we could have had the reverse as well, isn't it? But it has been set, so we don't need to fight over this, we don't need to have a debate over this. So what we need to understand is, if there are 10 coulombs and 5 coulombs, so 10 means high, 5 means low. If there is one positive and one negative, one positive will mean high and one negative will mean low. Is that fine? Because we talk in the context of the positive charge. Is that fine? Similarly, for example, in gravitation fields, if a body is here, it has low gravitational energy, isn't it? So it has less potential. If it is taken up, it gains potential energy, isn't it? It has more potential. Is that fine? So, similarly, low potential will be here, higher potential will be here. It is the same thing with regard to the charges. Is that fine? Now, there is a relationship between the work and the potential energy. The relationship is that the work done is always equal to the negative of the potential energy. Remember this. Work and potential energy are same. Work and potential energy are same, but by sign conventions they are opposite. Like for example, I will tell you. I told you, if there are two positive charges here, what is their natural tendency? To go away. When they have the natural tendency of going away, that means their potential is high. So it is positive. Is that fine? Because high is taken as positive, right?
Yes.
Clear? But to keep them here, you have to do work like this. So it is against the potential energy, isn't it? And against means negative. Is that fine? I'll repeat what I said. I said when there are two positive charges very close to each other, they want to repel. They have a general tendency to perform work, and that work, that tendency is to go away. When the tendency is to go away, it means higher potential, right? Right? So when there is higher potential, that means there is higher potential energy. Fine? But when you are doing work, when you are performing work from outside, to keep them here, you have to perform work like this in the opposite direction. So that work is against your potential, isn't it? Therefore, the sign convention says work and potential energy are equal but opposite in their directions. So we have to take it as negative. Is that fine? Okay, then we have some equations because that will be used in the questions. Electric potential energy between two like charges. Say for example, we have two like charges here. Okay? And okay, we can also do one thing. We can say that it is equal to the negative of, what is work? You know that work is equal to force multiplied by the distance, isn't it? Yes or no? So you can take that expression as well. You know that force between two charges, I told you it is equal to gamma q small q upon r squared, isn't it? Multiplied by r. So r and r will cancel out. We will have a general expression for potential energy, and that will be gamma charge, another charge divided by the distance. That will be the general expression. So here, if we have two like charges, the potential energy between them will be given by the same expression, gamma capital Q small q upon r. That will be the expression for the potential energy for two like charges, okay? But if the charges are opposite, that means one is positive, another is negative, the potential energy will be negative gamma q upon r. And here you need to understand, very important thing, this is positive because the general tendency is to go away, it's higher potential. Here it is negative. Why? Because the general tendency is not to go away, it is to come closer. Okay? Because the direction is important, so we give it the negative sign. This is for opposing charges, yes. And the general formula is always this. Potential energy in general is equal to gamma q1 q2 upon r. Remember, this is the general expression for the potential. Fine? We'll be using this in numericals. Yeah.
What's the last one?
General formula, yeah. It's a general formula. For two charges Q1, Q2, you can always use this expression, okay?
And the other one was only for one.
No, this is actually the same. All the three are same.
No, the work and potential energy.
Yeah, that is a relationship. Work and potential energy are the negative of each other but equal in magnitudes.
Can I go down a little bit? Yes. No.
I feel like a traffic police regulating the circle. Yeah. The distance is R. No square in the distance. That is for the force. If it is square here, okay, then it is for force. But we have potential energy. It doesn't have a square in the distance. Okay, let's try to solve this numerical before we finish. An electron is released from rest in a uniform electric field. Do you know? I have told you how to represent a uniform electric field. Uniform. The field lines have to be equally spaced, isn't it? Say for example, this is a uniform electric field. The question says an electron is released. That means there is an electron which has been placed inside the electric field. So what will happen to this electron? Yes? Electron is negative, obviously.
Then it will go against the...
Exactly. It will experience a force, right?
Yes.
So this electron will experience a force, something like this, against the electric field, isn't it? And that force will be given by, yes, negative E multiplied by E, isn't it? Isn't it? And it will be like this.
The field and then the electron.
Yeah?
The field and then the electron.
Yeah. The electronic charge multiplied by the field, isn't it? The question is, what happens to the electric potential energy of the system? See, initially, when the electron was placed, the potential energy of the system was maximum. And that potential energy is getting converted into kinetic energy, isn't it? Because when there is force, so due to this force, the initial velocity was 0, isn't it? Yes? So this will get converted, this force will create acceleration. And you can find the acceleration. You can say mass into acceleration is equal to negative E multiplied by E, due to which you can say acceleration is equal to negative E multiplied by E upon m. This is the acceleration. That means the acceleration is like this against the electric field. So we have the acceleration, right? Initial velocity was 0. Due to which we can have some other velocity. Velocity is continuously increasing in this direction. Is that fine? So we can say v square minus u square is equal to twice as. We can use this expression, right? Or you can also say final velocity is equal to u plus acceleration multiplied by the time. So you can find the final velocity. When there is velocity, that means there is what? Kinetic energy, isn't it? Yes or no? So what we can say is, the potential energy of the system is decreasing because the charge is going away. Okay? It is going away. And it is getting converted into kinetic energy slowly. Is that fine? There will be a time when all the potential energy of the system will become 0, but it will be converted into kinetic energy without any loss of energy. This is as per the law of conservation of energy. Remember this thing. The law of conservation of energy always holds good when you are talking about electrostatic fields. All the potential gets converted into kinetic energy, so the body will have some velocity. You might be asked in your exams the question, after 5 seconds, what is the velocity? First find the acceleration, find the time, and then multiply. you can be asked how much distance will it travel within this time. So you can then use the another equation and find the distance as well. Is that fine? First copy this and then you can write down a question. Today's 5.
Yes.
Done? Write down the question. An electron was released. An electron was released in an electric field of strength. An electron was released in an electric field of strength 50 newtons per coulomb. 50 newtons per coulomb, okay? Full stop. After being in the field for 10 seconds, after being in the field for 10 seconds, find the velocity gained. Find the velocity gained, comma, the momentum, comma, kinetic energy, and the distance traveled, by the electron. Try to solve this question. So there is an electric field. There is an electron inside. The value is 50 newtons per coulomb. Electron will experience a force like this. So you are asked to find what are the various things that you have to find. You have to find the velocity. You have to find the kinetic energy. You have to find the momentum. You have to find the distance. And you also have to find what? The velocity, kinetic energy, momentum. The time was given. How much is the time? 5 seconds? Yes, try to solve it. Which formula? You might use these formulas. Force is equal to Q multiplied by E. You might be using kinetic energy is equal to half of mv square. You might be using momentum is equal to mass multiplied by velocity. You might be using V is equal to U plus AT. you might be using V square minus U square is equal to twice A delta X. Fine? Allow that. They're playing with the car. May God give life to your car. Lamborghini, Mustang.
Yeah,
It can't really. All wheels. You don't know what wheels?
I know what to do.
They're burnt wheels. They don't know. Yeah. Good. Nice. What would you do? The child is teaching for them. It's easy.
No, it's not good one.
You find the velocity from the equation.
Which one?
Last one. What? 50 electric field.
How will I get it from the last one?
Yeah, U is 0, it is at rest. It was released. You find A first. See, this question is easy. Did it? Electron. Okay, the mass of electron. It is 9.1 multiplied by 10 to the power negative 31 kgs. See, first of all, to find kinetic energy, we have the mass, we don't have velocity. To find the momentum, we have the mass, we don't have velocity. So we have to find the velocity. And to find the velocity, we have to use this and this equation. Right? So we can use this equation, but to use this equation, there is another problem. We do not have acceleration. So first find acceleration. How do you find acceleration? You know that the force, the electrostatic force which gets applied to this electron is given by, yes, negative E multiplied by E, isn't it?
Yes.
But that force is also given by the Newton's second law, F is equal to ma.
Yes.
So therefore you will have acceleration, right? E upon m, isn't it? So try to solve it for the acceleration first. What is the charge of an electron? 1.6, 10 to the power negative 19, right? Times, what is the electric field? 50. What is the mass? 9.1, 10 to the power negative 31, isn't it? Now first give me the value of the acceleration, come on. What is the acceleration? Yes? Fatima, yes?
8.79
8.79
times 10 to the power of 12.
10 to the power 12 meter per second square. That's it. That is the acceleration. Now you have the acceleration. You put it here. You have the time. Initial velocity is 0. You find final velocity. When you find final velocity, you can find kinetic, you can find momentum, and also you can find delta x, isn't it? Khalas, that's the question. Is that clear? So rest parts are your homework. You try to solve it and give me the result. Is that fine?
Yes.
Raghal Puri is happy because class is over. Thank you so much. God bless you all. Yeah, thank you.